We've actually got 4 talks here in the afternoon, so there's a bunch more content to go over. It's really pretty interesting. Just by show of hands, I was curious, right? Because we've talked about, you can see that we brought a bunch of at-scale operators, right? And for me, this is my first time to work at an operator. My whole time in networking, I've been at vendors, startups, large. I was at Cisco in the mid-90s. So this is new for us, or for me, to be part of the operator community. So I was just curious. I recognize a lot of folks, but who here works for an operator? You are running a network, and you are on call possibly right now if the network is melting. Raise your hand if you're an operator of a network. All right. Be proud. Be proud. Yeah, so I'm assuming the other half, or the other 2/3, or roughly, work for different vendors at different levels, software, hardware. If you, all of this stuff is blurring. I think it's pretty interesting. One of the reasons that we bring the at-scale events together, right, is to bring the operators and the vendors together and really to collaborate, so you hear kind of what we're working on. Hopefully you all had some good conversations during lunch. I was talking to a colleague the other day about, she works in the supply chain for our company and for Facebook, and we've got, and some of you saw the 6-pack, and we were realizing just what a blurring is happening across the networking industry, right? Like, we have a supply chain group, which you may, and we're rolling out hardware, we're rolling out software, we're trying to contribute and work with everybody. And so I would encourage all of you to just participate very actively, especially if you're in the vendor community. We want to, like Najim said, get a dialogue going so that we can figure out how your products can plug in, how we can leverage them, because obviously Facebook, any of the large operators, we're not going to do it all by ourselves. Like, we want to write a bunch of it ourselves, but we can't do it all by ourselves. So that is the reason we bring up the operators here for all of you today. So with that, our first speaker for the afternoon is Artur Bergman, and part of the company Fastly, which you may have heard of, just rapidly expanding in the CDN space. You'll see actually all the talks this afternoon are a slightly different layer, talking a lot more about the interaction with the users, talking about the applications running on top of the network. So I think please enjoy and ask your questions of the speakers. So with that, please help me welcome Artur.
Hello. Hi. So Artur Bergman, crucially on Twitter, founder of Fastly. Come from a background of running large websites and building tools to run those websites. LiveJournal is where Memcache came from, so that's kind of, my heritage comes much more from the software engineering side than network engineering or operations. And if you have questions that are relevant to slides, like, feel free to ask them in the middle, or we have a Q&A session afterwards. So this is the only slide about Fastly. Fastly is a CDN. We are based on Varnish. And to give some context, we don't have a backbone. We're not like most of the other speakers that you will hear or have heard. All of our traffic goes to end users, basically. So no backbone, no central spines. It's all about delivering content to users from the edge as fast as possible. And we're specialized in small objects that are kind of semi-dynamic. So real-time purging is one of our key features, but it's all about real-time and allowing you to move things to the edge. And so most of our architecture has been designed with that in mind. So a Fastly POP looks like this and is basically built out of commodity hardware. So 10 cores, 768 gigs of RAM, and up to 24 terabytes of SSDs, actually. and we're looking to bring that even higher. But it is still commodity. And a rack is 16 machines, 4 switches, 16 ports for a machine, and 16 ports for an upstream, or 16 ports for upstream. So no oversubscription or very, very little oversubscription. We have 2 of those in a unit, so 32 machines. That's why we need a 64 ports. And you can see we're basically out of ports at this point. So with the size of the switch, we can grow the units. So that gives you 24 terabytes of RAM, 16 billion objects, about half a terabit of egress capacity for small objects, more like a terabit if you were doing large objects, and about 700,000 requests per second for 2 racks. So the evolution of a Fastly POP. Life used to be simple. This is literally the first Fastly POP. I took 2 servers, it was before Fastly even existed. I took 2 servers, checked them as luggage, and flew to London. And then I took a black cab to Docklands, and I plugged them in. And that was our first POP at Wikia. So, and hint, that is apparently a violation of lots of customs laws and tax laws and lots of other things, but I didn't know at the time. So Gen 1, and amazingly, I never got stopped, but the entire experience of running between the oversized luggage and the normal luggage and having $30,000 of gear coming out of one of them was pretty stressful. So Gen 1 was 2 machines per POP. We direct connected transit directly into the machines, and we did BGP of the machines. We could do 20 gigs per second, 50,000 RPS. And that was plenty at the time for us. And it was easy to manage, but it doesn't scale, right? Like, as you add more machines, you need the same number of transits. Transit providers do not load balance inbound traffic very well at all, or if they do it at all. And it's very vulnerable to DDoS because you have the link IP. You can take a machine out pretty easily, even if it's a 10 gig port. So we went for Gen 2. And the criteria was no routers. So I've spent far too much money in my life on real routers. It's just we're not going there. No load balancers. I fucking hate F5. And I've spent so much money on them, and they've paid those devices have paged me so many times that no. We needed to scale out, but we still needed BGP to the server, and I'll come back to the BGP to the server later. So we put an Arista switch in. We used VRP and Keep Alive D. We put more than 2 machines. Initially 2. We added more. It was really, really fragile. It kept falling over because VRPD or Keep Alive D isn't actually that good. And it's very, very easy for an operator to make a mistake. So the other problem is we need BGP to the server. And getting multiple BGP sessions for one link from transit providers is impossible, because I guess they don't actually know how to operate things. So the Gen 3 design, we switched to ECMP on the inbound, BGP on the switch, and we reflect down the entire BGP table down to the machines. So there's a clear boundary between us and the upstream. It's not actually that clear, but it is much clearer than it used to be. So then we need Gen 4. We need to scale out even more. So the criteria is we need multiple racks. We can't be tied down to one rack. We need higher availability, but we don't want to overinvest in gear per rack. And we need to scale out more. So we did a design that was initially 3 racks with a switch in each rack and a loop. Each ISP was connected to each rack, and BGP to each switch, and then we reflected down, but only from the local switch. So we were fucked. That was a horrible, horrible, horrible design that caused us a lot of problems. So at the core, you have something like this, right? And it just doesn't work, because when you have a break, you're out of east-west capacity, right? It just does not work. So loops are bad. We had split brain all the time. We had latency problems as soon as we hit any east-west bandwidth, and then the entire POP would start degrading. And you need way more ports than we wanted to spend on this. So that was, don't do this. Like, it just did not work. And it took us a year to dig out of that hole. So the criteria for our Gen 5 design was, the first one was easy to operate and forgiving to failures. Right? Like the previous ones all had a problem, like it was very easy for an operator to make a mistake, and even if that mistake was very small, it would have pretty drastic consequences. And we needed to make sure that that did not happen. And designing for ease to operate, I think, is really, really key. And I think networking gear traditionally has been really bad at doing so. How many people have locked themselves out with little ACL change, right? Or similar stupid changes that it doesn't help eliminate. The other way was eliminate east-west, right? Like most of our traffic is actually north-south, and so why have any east-west if we can get rid of it? We also got tired of N2 for networking gear and wanted to move to M+1 for cost structure and for various other reasons. And we need to support up to 32 machines in a unit. So each machine is connected to each switch. There are 4 switches. So that eliminates east-west. There are 4 total independent networks, which is M+1, and has actually been part of the easy to operate is moving to 4 completely independent networks. Because if there's any problem on the network, you take that side down and you don't worry about it. Right? There's ample capacity across the 3 remaining networks that you don't have to troubleshoot while production traffic is flowing over the network, and that is huge. That's actually one thing that's really nice about running a CDN, is if a POP is having problems, you can just send it somewhere else and then debug it without live traffic being hurt during that. Another great aspect of being a CDN is that you can throw customer data away and we just fetch it again. So highly recommended compared to running large database clusters. Also, fantastic way of just testing new stuff. So we ended up with 4 networks, IPMI, management, and the 4 10 gig networks. So this is one of the racks from the Gen 5 design. So you can see each rack has 2 switches for the actual backbone, and then a management switch underneath. And then there is the rack next to it, even if it's empty, with servers, we'll have 2 switches because they're pre-cabled, so we can just fill them up. And the resiliency, I mean, it's worked extremely, extremely well. Those POPs have enough internal redundancy to survive most failures, and also very, very easy to operate. Bao, who is one of our network engineers, might disagree with me, but compared to previous generations, very easy to operate. So what we actually have is distributed routing, right? I don't want routers. They suck, right? Like every place I've been, they've always prevented me from doing something I wanted to do or cost a lot of money. But I think more so than expensive, the loss of control and the loss of visibility in the network is much higher priority for us than the money. The other is that I want to blur the line between a network engineer and a systems engineer, because really the best way to debug problems is across that boundary. So no routers, like Cisco and Juniper has gotten enough money out of me. However, routing is still needed, right? Like we still need to route. Aristas do not hold the full BGP table. So what do? We run Bird on the Aristas, and we route reflect down. And so you end up with 2.5 million routes on each server, right? That's Facebook's IP. We're reaching it over level 3, and you have multipath. Or you can do show route all for that, and you get all the data. This is actually run on a server. That's the, there we go. So the flow is really simple, right? Into the switch, all the transits. From the switch to the server. from the server into the kernel. The server gets it from 4 upstreams, so it injects 4 routes. If it has it, if it's only on 2, or if it's one transit is down on 1, it ends up not being 4, it ends up being 3. And then we just multipath out, and let the kernel choose our next hop based on the routing table. And the kernel is, that scales much, much better than expensive cores or edges. So there are some problems with this. One is you need static ARP assignments because we can't ARP next hop. But the benefits are really, really, really large. So I don't know, does anyone here run full BGP tables on servers? Like, it works great. Like, it's an amazing power and amazing flexibility. And so an example of that is our tool STPing. So this will simultaneously ping over all upstreams available to whatever you want. And it will show you the L3s are marked because that's the actual preferred route. But you can just keep this running and see what's going on. And this is really, really hard to do with a conventional architecture. Like, it's possible, you can use QoS tags to do policy routing on egress and so on, but it is really, really hard and much more complicated than just having these 16 next hops on the server. As you can see, we should have used Comcast to reach Facebook, not level 3. So we had an issue in London. Like, our level 3, I shouldn't have said that. One of our transits had a higher RTT than most of our other transits. And we looked at it and couldn't figure it out, and we realized that one of them was being backhauled. One of our ports in London was being backhauled back to Paris, and then egressed up back to the UK. And so if we had a traditional architecture, it would have been extremely hard for us to determine that this next hop was actually causing problems and not the transit provider itself. So we also have this tool called StMTR, which does the same thing but MTR. So we'll run parallel MTRs for you, giving the actual routes. And again, nearly impossible to do in a traditional architecture. Like, I can see ways of doing it, but it would be really, really nasty. And incredibly easy for operations engineer or network engineers to debug in the middle of the night. Like, it qualifies for the 3 a.m. like pager, oh shit, I'm tired, I need to debug something. The other cool thing is it actually gives us benefits up in the stack, right? Because we have all this information inside our routing table. So if I go back and look at this one, see the metric field, 32934? That's Facebook's AS number. So one of the things we did is we shoved the AS number into the metric field so we can access it from inside our application. So we can now very, very easily, instead of relying on a static database of AS numbers, we can just pull it out with a kernel call, right? And so that's an example of data we can then elevate up to our application layer to do much, much better decisions. Also, does anyone work for a transit provider? Okay, good. Because, wow, they need to get their shit together. So we use Varnish. Varnish has this feature called VCL, which is how you configure it. And so what we can do is literally say, like, we can tell the client, the HTTP client, what the next hop is, right? Because we can look it up. We know what the next hop is. Or, even cooler, this is not actually exposed to customers, but even cooler, by sending us a magic header, you can choose which outbound path to take, right? So you're doing the policy routing throughout the entire stack, but like on the machine itself, instead of complicating it and having to do things at the edge. And that's kind of what I mean with the entire stack is a distributed router or distributed routing as a service, I don't We also expose packet loss and RTT data, and we can get per connection. And this also becomes more valuable because we know the next hop, we know the AS path, so we can do really, really cool things. We have a patch in our public repo that extends TCP info to actually include the next hop for a given socket, because if you look it up, you won't be able to tell otherwise. So, despite my spelling of it, I actually like Redshift. So we feed a lot of data into it. And I wish I could actually say the next top AS numbers here, but since one is 3 and one is 4, you can maybe guess. And 7 and 1 is Verizon. So one of our providers, as you can see, at 8 p.m. has clear congestion to Verizon, and one does not, right? And we can actually do this data processing both post, but also in real time, and go like, hey, we want to send a sample of the traffic over another transit provider and see what happens. And that would, again, be very, very hard to do in a more traditional environment. And yes, 3.1% packet loss is pretty horrific, though not at all the worst we've seen. So let's just be clear. Software-defined anything means we're so fucking tired of the vendors fucking up our software stack, we want to write it ourselves. Like, that's all it means. Like, software-defined storage, I'm tired of NetApp. Software-defined routing, like, I'm tired of Cisco. Like, it's just moving it up to a level where we can control it. And so we did it by moving as much logic we could to the servers. And that's worked extremely, extremely well. And the servers have, like, the lookup on the routing table is not at all a expensive or any substantive part of the CPU usage on the servers. It doesn't show up. So we go to the next one, no load balancers, right? We are at the edge, so we get DDoS. We get DDoS a lot. As soon as you have state, you fall over in a DDoS, right? And any hardware load balancer out there basically has a finite amount of state, and then it falls over. They're also expensive. Also, no OpenFlow. Like, it just doesn't fucking work. Right? We tried it, it doesn't work. I don't know anyone who really successfully uses it as designed, especially at the edge. The latency is high, the state is bad. So what we ended up with was ECMP. Right? All servers advertise the same ranges. The switch hashes flows, and it works really, really well. Like, there's no state. Yep.
Same problem. Similar setup. But if for the ECMP one hash X, you can do like reset all the TCP connections.
I'll get there. So the question was, what happens when you reset all the TCP connections? And it's difficult. The other big problem is ICMP. You get an ICMP message back from an intermediate shitty box, and it will route to the wrong server. And we see a lot of very, very bad middle boxes. So what we do there is we have a very wide ECMP table. Like, if a vendor would give us 1,024 ECMP entries, I would take it. Right? Ideally, you want, if you have 32 servers, you want 994 entries, 31 entries per server. And then, when a server crashes, instead of rehashing, you just move those entries to other servers. And the more entries you have, the more fine granular the load distribution gets. And the way we do this is by having lots of fake MAC addresses per machine, and then fake entries in the ARP table on the switch, and then a very wide routing entry for the ECMP. So it turns out the MAC, like, the entries, the IPs don't actually need to exist, right, as long as the ARPs are responded to. And this works great, like a server. But if you want to drain a server, you still have a problem, right? Because you take the server out, you break all the connections. So the way we do graceful failover is by moving the connections around. And the servers basically go, hey, this is a connection I didn't know about. I'm going to look at the MAC address, and I'm going to forward the request back to the server that was actually supposed to serve this. right? So that's what the 0101, and that means that this is server 1, and it was expecting it was server 1. If it was 0102 and it didn't know about it, it would send it off to server 2. Right? And that way, like we can drain a server and not break connections. A server can crash, not break connections, and it works really, really, really well. We also have, it basically becomes a distributed load balancer where the server and the switch or the load balancer communicate with each other directly or indirectly to give you all the features that otherwise would be centralized. And there is state tracking during a controlled failover event because it needs to track, but that tracking is distributed across all nodes and much, much simpler to do, right? And also doesn't use SRAM in a table on a switch. It uses main memory on a machine that is so much cheaper, and also we have 768 gigs of RAM on each machine. The other problem is ICMP. We just broadcast them. Machine gets an ICMP message that matches that, type 3, code 4, and isn't marked with a TOS. We just broadcast it to all other machines. And the TOS is important because otherwise you will loop. And we set the TTL to 2 because otherwise you will generate too much traffic. This also works. Like the kernel looks at it and thinks it's destined for itself and adjusts it. And the gateway there, 10.11.12.0, is actually a permanently added ARP address to FFF, right? So it just multicasts it out or broadcasts it out. So we have distributed routing, distributed load balancing, and a very, very easy short path from our servers directly out to the internet with very, very fine-grained control of what we do. And we defer as much as possible to software. Right? Like we use Arista heavily today because they give us off-the-shelf hardware that we have very, very good control over. But I would love to move to more different platforms as long as they can give me that control that I need. Because I'm a software engineer. I like writing software. And if I can control it from software, it will work better. So, any questions? Yes?
Was there no topology out there that mapped to the requirements you had that you had to go through this whole process? Like an Akamai or any other number of pre-existing CDNs?
So the question is if there was a topology that matched what we wanted. So in this space, it is very, very good to be very careful with how much information you read about certain competitors that are very happy to use their patent and trade secret and copyright and all the other aspects they have to hit you hard. So that's one reason we didn't want to look at how certain other vendors do it. But I think in general, excluding Akamai, which I have great respect, it's a software engineering company. All other CDNs are network companies, and they're run by network engineers. So here's what happens. I'm level 3. I have tons of fucking transit. Oh, wait. I want to use it. I'm going to buy 100,000 servers because I can only get a shitty performance out of each server. And now I have a massive networking problem. But guess what? I know how to solve that. So they solve problems by throwing machines at it. So they don't have the same throughput per server and the same kind of east-west traffic that ends up happening. So none of those really match what we wanted. And they're also typically based around large cores and large peering routers. And one of the reasons we do have such a lot of storage and RAM per server is because we do long-tail content really well, and that just ends up being a lot of content, and the less we have to go between servers, the better. So.
Hey, Wallace from Google. Thank you very much. Very nice talk. I had a question about the way you do the next swap selection. I'm curious about perhaps I missed some details. I think you're choosing the NESOP from the software. Is it some fancy kernel interface? How does that piece work?
How it actually selects it?
How does it inform kernel application?
QS tag to the kernel.
And then you do FW marks or something like that?
Yeah, sorry, not QS. Yeah, it's a mark. You mark it with whichever upstream you actually want.
Okay, thanks.
How do you add servers in your MAC address spoofing thing? Like how do you shift load to a new server?
To a brand new server?
Yeah.
Typically, when we expand a POP, we take it offline during nighttime while we add the new servers. There's also a rebalancing that needs to happen.
Yeah, for your ECMP.
Well, also for the content.
Yes.
So, and when you operate around the world, right? Like at 3 a.m. in Germany, there's no traffic, so you can just do it then. So.
You hate F5, so do I, for a different reason anyway. So what was the load balancer mainly used for F5? Was it just for an L4 load balancing, or did you use L7 policies, SYN cookie protection, and those things?
That was not at Fastly, that was in my past lives.
Okay.
And unfortunately, it always started at L4, and then it ended up in L7, and then they fell over.
So you don't use any of the L7 features?
We don't
all that is offloaded at the back end, or?
So, I mean, everything in Fastly is done on the servers.
Okay. Thank you.
All right. Well, then please, again, thank you very much to Artur.
Thank you.